Good afternoon once again. We are here again for our unit on electromagnetic field theory. And maybe before we continue with our class, in our previous lesson, we looked at vector analysis, and in vector analysis, we look at unit vector, we look at coordinate system. Those were the major things that we looked at in the previous two lectures that we did. Today, we are going to proceed further with part of vectors, but we are going to look at vector calculus. Calculus. And under vector calculus, we are going to concentrate majorly on how differential vectors are done. We are going to look at majorly differential length, surface, and volume. We will also look at integration of vectors. Integration, and basically we are going to measure on two basic theorems in vectors, and these are we have divergence and Stokes theorem. And finally we look at some few examples that are related to all these. So without further ado, we'll start our lesson for today. So without wasting time, we'll just have our differential. Differential length, area, and volume. So we can say that differential elements in length, area, and volume can be defined in one, Cartesian. We are still looking at our coordinate system. Cartesian, two, cylindrical. Then finally we had our third as being what? Spherical coordinate systems. So now we want to look at these differential length, area, and volume, first of all in Cartesian coordinate system. So we can start with our first one and say that Cartesian coordinate. So in our Cartesian coordinates now, we can say that the first one is, maybe before that we can say from the figure below, So from our figure, we can have our figure here, and we want to draw that figure in our Cartesian coordinate system. So we say that we're still using the right-hand rule, like so, where this is still Z. We have our Y there and X, so that we can have our surface here. like so. So we have that, and then we can name our coordinates. This be A, B, not ordinate, but the points A, B, C, D, and also the back point has P, Q, R, and S. So that length along the y-axis, this will be named as dx, dy, sorry. So it's a small differential length. So we are calling it as being dy. And the length that is along the x-axis, that particular length we'll also call it as dx. And the one that is parallel to the z-axis, this particular length, we'll also call it as what? dz. Yeah? So then we can come to our now differential length. So as the first one here, Roman 1, we can talk of our differential length. Differential length. Now we'll denote length with what? dl with a bar on top. That indicates that this is a vector actually. Yeah? So it's a vector with magnitude along the x-axis, y-axis, and also the z-axis. So along the x-axis in that order of Cartesian, which is x, y, and z, so we are saying that along the x-axis we'll have dx with a unit vector of ax bar. Along the y-axis, we'll have dy with a unit vector of that. And along the z-axis, you're also going to have dz followed by a unit vector of what? Az bar. So that is how we always represent our differential length. Then the second one, because we mentioned differential length and then also differential surface, yeah? Differential surface. That was my differential length and differential surface. Now, this one is based on a particular surface. If you look at this keenly, then I have my surface A, B, C, D. This surface has a unit vector that is perpendicular to it. So that particular vector that is perpendicular to this surface is in the direction of AX. So, in the direction of AX, my particular surface will be, you see, surface is area. So area basically we have to multiply length times the what? The height or the width. So my length here is DC, my height is BC or AD, which is the same as DZ. So if I'm looking at that particular surface, then along the AX, I'll say that DS bar, S stands for surface, L was supposed to represent what? Length. So DS bar will be given by this length, which is dy multiplied by dz, which is our height now, that particular one, so that we can get a differential area or a small area in the direction of what? AX bar. Now, similarly, in the direction of y is this particular surface. So you can see that is also a vector because they have direction. Yeah? If I'm looking at this direction, the unit vector normal to the surface is AX. The unit vector normal to this surface is what? AY bar. So that particular surface is this length times that height. So we have that particular surface there. So now if I was to look at that area of that differential surface, then I'll have my DS bar along the AY direction as being dx, dz in the direction of AY bar. Similarly, if now I'm supposed to look at the other surface, because we have this, there are actually 6 surfaces. Yeah? This other one, which is now like our top of the cube. So this is in the direction of AZ. So in the direction of AZ, I have that length and this length. So this length is the same as dx. So we are going to have dx, and this length is the same as dy times dy in the direction of AZ. So that is my what? ds in the direction of az. It's very important to note all this because we'll be using them. You see, when we'll be doing our integrals, we'll be integrating a double integral with respect to y, with respect to z, with respect to x, with respect to z, respect to x, with respect to what? Y. So now this is how we look at our surfaces on a Cartesian coordinate system. Then next is the volume, because we are talking of differential length, surface, and volume. Our differential volume, again, the third one, Roman 3, differential volume. So our differential volume dV, if I go back to my drawing, will be represented by, so we want to get the volume of this cube. And if you are to get the volume of the cube, then definitely it must be length times width times what? Times height. So differential volume dV must be the same as dx, dy, dz. Yeah? Later on, we'll realize that this will prompt us to do a triple integral here when you're dealing with this kind of a surface, a volume, sorry. Yeah. And again, something very important that we need to note. If you look at differential volume, I've not indicated a bar on top, meaning that volume is a scalar quantity. A differential volume is a scalar quantity, unlike length, which is a vector, and surfaces, they all have bars on top because they are vector quantities. Then apart from that now, we can also look at how we can represent our differential length, volume, and area in our what? Cylindrical coordinate system, yeah? So the second one, we are saying a cylindrical coordinates. Cylindrical coordinates. So again, we need to draw so still this is z, y, and that is x. So I need to draw my cylinder like we did previously. That, we have that, and then from there I need, so that I can have that. So that we have that. So we have our drawing, a cylinder with a small volume here, a differential volume. So now we want to mark our length first so that we can be able to do what? Find our differential length, area, and volume. Now, if this be my radius rho, so this is my radius rho here, and we have our angle phi, and we also have the height of the cylinder here indicated as z, like so. That is the height of our cylinder. Now again, very important to note that we have a unit vector in this particular direction, that is along the rho axis, that will still be a rho bar. And along the curve here, which is that, this will be a phi bar. And the height, which is our z-axis. Remember, in cylindrical coordinate system, we are talking of rho, phi, and what? Z. So along the z-axis, we have a unit vector, which is what? Az bar. So all the three unit vectors are actually mutually perpendicular, meaning that they make an angle of 90 degrees with each other, like so, yeah? So we have that. So we are interested in this. Now, this being a small volume, that length that is along the rho, this will be called as d rho. Similarly, the height of our particular volume, which is that, and it's along the z-axis, this will be dz. Now, the challenge comes in labeling this particular part. That's not a big problem, but we can look at it together how we can get this particular length. If we remember how we get our circumference from our lower level, we did this maybe in our basic mathematics. We have that is the center of a circle. Let me assume that my length here is rho, my radius is rho, another radius there is rho, and this is my angle, which is also what? Phi. So if I was to get this particular length, let me call it as dl, it's a small length section. If I was to get that particular length, dl, then we can say that our dl, or rather the length L, let me call it L for now, L must be given as phi over 360 degrees multiplied by 2 pi. Yeah, phi over 360 degrees multiplied by 2 pi times the radius rho. But now assume that this particular length is this particular length here, a very small length that we are calling as what? D rho. Similarly, this other radius also is d rho. And the angle, it's not theta, but not phi, but d phi. Yeah? Then I can change all this such that that particular length, now I'll call it as dl. So dl must be what? Instead of phi, we'll have d phi all over 360 degrees multiplied by 2 pi d what? D rho. That is what we are going to get as our length dl. Now, instead of using the whole circumference or the whole circle angle as 360 in degrees, we can change this to be in radians, such that we are going to have what? In radians, this can be represented as, yeah, there's something I'm looking at here. Just a minute. And now let us use the length as being d rho. So no, rho and not d rho. So this is rho and not d rho, because it's a whole length from this point to this point, not this alone. From this point to this point. It's only the angle that is very small. So this be rho. So what you are saying that now, if we change this to 300, from 360 degrees to what? To radians, then we are going to have what? This will be d phi all over 2 pi multiplied by 2 pi rho, such that my small length dl, therefore I can say that dl can be represented as what? This value and this value will cancel, and I'll have it as being rho d what? D phi. And that is how we are able to get this particular length there. So this length, which is this, is rho d what? D phi. So this here can be indicated as rho d what? D phi. I hope you've understood how we are getting that particular length. So then now we can write our differential length, our differential surface, and our differential volume for cylindrical coordinate system. So if we are supposed to start with Roman 1, so let us have our differential length. And don't forget, length is a vector quantity. So remember, we are supposed to consider rho, phi, and z directions. So in the rho direction, our length is d rho. This is our length in the rho direction. So we are going to write that as being d rho in the arrow direction. Now again, the next one should be phi. Phi is tangential to the curve. It creates a tangent to this curve. That length that creates a tangent to the curve is what we are trying to find out. This is what we were calculating. And so we are going to have that as being what? Rho d phi in the a phi direction. And similarly, the length that is along the z-axis, it's one parallel to that, and we are saying that this length will be what? dz in the az direction. Now, and then the second one now, we are supposed to look at the what? Differential surface. Differential surface. Now, again, differential surface is a vector quantity, so we are interested in the ds and the normal or the unit vector normal to that particular surface. So as usual, still we start with that surface that is in the arrow direction. And this being my arrow direction is that. And that particular surface in the arrow direction is this one here. Yeah, that is our surface in the arrow direction. So what are the lengths in the arrow direction? I think it's necessary that we have a small drawing. This is what we have in the arrow direction. These are the surfaces. That is the particular surface in the arrow direction. This is arrow direction. And that surface has a height of dz. And the particular curve, that curve is this curve here, and it's also the upper curve. And that curve is given as rho d phi. So this is our surface. And that surface then, if we represent that, then we are going to have what? We'll have rho d phi d what? dz in the arrow direction. That will be our particular surface. Then next one is that particular surface that is in the phi direction, that is along that. You see, the surface that is hidden, it's the same as this particular surface, but it's the one that is on the other side of the board that we are not seeing. So that surface, if we are to draw that, then our particular surface in that direction is going to be this surface. In the arrow direction, we have that particular one. That is our surface. And that surface has a height of dz. And this is what? D rho. The direction is inside going that particular way. That is our a phi bar. So this is our surface. And then in that particular surface, again, we can say that our ds bar will be given as what? It will be d rho, d what? dz in the a phi direction. So those are our surface that we've represented so far. Then finally, we have our final surface now that is in the z direction, which is now the top. This top is what is in the az direction. It is parallel to this. So that is what we have. Again, if we are to draw that, we have this section there, then we have that, and we have that, and that. And this is the particular surface in the az direction. So the length from here to here, or from here to here, is what? D rho. And the particular curve that we have must be rho d what? D phi. So this surface will be represented as ds, which will be the same as, I'll start with this rho. So we have rho, d rho. Then we have d what? D phi in the direction of a z. So these are the three surfaces that are there in cylindrical coordinate system. So we have that, we have this, and we have this. So you can see also their direction is in the arrow. We have in the phi direction and in the z direction. Then finally we have our differential volume. Yeah, differential volume. And remember, volume is a scalar quantity, so we are only going to multiply all the what? The lengths. When you're trying to find our differential volume, we'll just have dV. If we multiply all the lengths, we have d rho, we have dz, and we have rho d what? D phi. So if I start with that rho, it will be rho d phi, and d what? Dz as being our differential volume. Then we've looked at the two coordinate system. Then finally we have the what? Spherical coordinate system. So the third one is a spherical coordinate coordinate. So then we have to draw a hemisphere or a half sphere. So we have our hemisphere and we have our volume. So still remember our coordinate system that we had in what? In spherical. So in spherical we talked about r, theta, and phi. R, theta, phi. So still the axis here remain as z, and still we have y axis, and we also have what? Our x-axis. The angle that x-axis makes with the radius of the sphere still remains as phi. The angle that it makes with the radius, this is the radius of the sphere on the azimuth, is phi. Along the vertex or the z, this angle here is theta, and the whole radius is r, but this portion of the radius, because it's a small section from here to here, must be dr. Then again now, we have that as dr. Yeah, this, because being a small angle now, up to that point, that will be d theta. We have d theta there, and still the same procedure that we used to find the other curve. So we are going to apply the same procedure of finding the curve. So I'm not going to go through it again because we've done it. Now this section here, the length from this point to this point, again, if you use the same procedure now, if the whole length from here to here is r, yeah, this is r, then this must be r d what? D theta, this particular length here. It is r d theta. Then we have that radius, we're still having it as rho. Rho is our radius. This small section here, it has an angle, and this angle also is d phi. This angle up to there, it is d phi. Remember to distinguish between theta and phi. Theta and phi. Yeah? This is theta, this is phi. So this angle here is phi. The whole radius from here to here is d what? Is rho. So it means that this must be rho d what? Rho d phi. And that is the same as this, which is this, and you're saying that that is rho d what? D phi, yeah? Yeah, let me just have it up here because this space is so squeezed a bit. So I'm referring to this. That is rho d phi. And we had represented rho previously in the other lesson when we were looking at our coordinate system, how we relate cylindrical versus spherical system. Now instead of having rho, remember rho is not one of the terms here. There was a way we represented rho in terms of what? R and the angle. So rho is the same as R sine theta. The what now? This is rho, but we have rho as being R sine theta. And we have to include that as being what? Our d phi. So now these are our lengths. So we have this, we have that, and we have the length dr. So then we can be able now to represent them. Represent length, differential length, differential surface, and finally differential volume. So let us start with the first one, yeah? Differential length. So differential length, dl bar. So we have to follow our coordinate system or our coordinates. So in the r direction, we have dr. So that is going to be dr in the ar bar direction. Then next, in the theta direction, look at this is our theta. Yeah, you see, I had not indicated that, but this is the tangential component in the a theta direction. That is our unit vector. Again, the unit vector in the r direction. Now, this being our r, so this is r also. This is a r, and the unit vector that is along the curve. This curve now will be that. This is the curve. So we are assuming that we have a unit vector, not assuming, but there is a unit vector in that direction, and that will be a what? A phi. So we have that in the AR direction. Now next is in the A theta direction. So the A theta direction is along it's tangential to the sphere. So that if we represent that is tangential to the sphere, we can see that particular length is RD theta in the A theta direction. Then finally in the A phi direction, then we are going to have what? What we had computed here, which is R sine theta d what? D phi in the A phi direction. That is how we represent our length, our differential length in spherical coordinate system. Then next we are going to represent our differential what? Surface here. Differential surface. Now once again, now if we are to represent our differential surface, I'll prefer we do the small drawings. Now this is our surface there. The first surface, we have that. I have another one. In the A theta, we have the base, which I'll equally try to draw. The base. Then in the A phi, A phi is this other one. If we do that, we have that, we have that, we have that. I'm just illustrating these three surfaces so that you can be able to look at our drawing in 3 dimensions. Yeah? Now, let us have our first. This is our surface first in the AR bar direction. Yeah? It is this particular surface. This is what we have. Let me just delete this other one so that it's easy to indicate them. This is the one that is normal to this particular surface or perpendicular to that particular surface. So that is what we have. And if you look at it keenly, here it is RD theta, and this particular point here is the same as R sine theta d what? D phi, that one, yeah? So this surface in the AR direction ds bar will be the same as what? R squared sine theta d theta d what? D phi, in which direction? AR bar. That is what we have as our particular surface in that direction. Then our next surface that we are supposed to look at is this other surface, which is this. This is now the A theta direction, yeah? The one going downwards, like that, yeah? So this is our A theta direction. And if you're keen with our A theta direction, we have dr, which is this length, and we have also this particular point, which is this. So this portion here is dr, and this portion here is what? R sine theta d what? D phi, not d theta, sorry, it's d phi. Now, if we represent that again in the, it's now the one going down in the A theta direction. This is theta. In the A theta direction, then what are we going to have there? Our ds must be R sine theta dr d what? D phi in the A theta bar direction. Then finally we have this particular surface, which is this. Well, it's the other one hidden on the other side of the board, the one we are not seeing. This one is opposite. The vector that is perpendicular or normal to this particular surface is the one moving outward the board. But we are interested in the one that is moving inside there. So if we represent this, we'll have to give it a negative vector. But the other one that is inside the board is a positive. Because if you look at this direction, it's like we are going towards the board, yeah, for that particular surface. So we are interested in that surface, but the one that goes inside the board. So we have dr, and this length is that length, and r d what? D theta. So that particular surface will be represented as ds bar to be the same as r dr d theta, in which direction? In the A phi direction. This is A phi inside the board, like so. So those are our three differential surfaces together with their vectors. You can be keen and look at what I'm doing here. We have bars on top to show that these are all vector quantities. Yeah? And then finally now we can have our differential volume. Differential volume. So our differential volume dV will be given as what? So differential volume dV is just a matter of multiplying all the three lengths. So we have r d theta, we have r sine theta d phi, and we have dr. But follow this order, yeah? So we are saying that how many r's are there? We have this r times this r will give me r squared. Then we have what again? We have sine. So it is r squared sine theta. So I've multiplied that, I've multiplied that, I've multiplied the sine. Then I need to also multiply what? dr. Then I have d theta, and I have d what? D phi. This one has no direction. So that is what we represent. That is how we represent our what? Our differential volume. So this is how we can represent all our what? Our three differential lengths, area, and volume in Cartesian, spherical, and cylindrical coordinate system.